The mathematical theory of probability begins with the Kolmogorov Axioms. Given a sample space S and its power set P, a probability measure is a function that maps the power set to the interval 0, 1, satisfying the following relationships. For any event, our probability is a real number between 0 and 1. The probability of the sample space itself is 1. And for any sequence of mutually exclusive events, the probability of the union is the sum of the probabilities of the individual event. Now let's go through some immediate consequences of our definition. So first, note that the empty set intersected with the empty set is the empty set. And so by definition, the empty set and the empty set are mutually exclusive. But their union is also the empty set. Now, this seems to be a lot about nothing, but it does have a point. Let the probability of the empty set be some real number x. Then the probability of their union, because they're mutually exclusive, is the sum of the two probabilities. But the union is just the empty set, and so now I have an equation that tells me x equals 0. And this gives us our first useful theorem. The probability of the empty set is 0. We can also use our definition more constructively. Let S be our sample space, and let's suppose the probabilities of two events are given. Do we actually have a probability measure? And the important thing here is once we add a few restrictions, we are no longer free to choose any values that we want. So the first thing to note is that any event can be broken up into its mutually exclusive outcome events. So the probability of the event A, B is the same as the probability of A plus the probability of B. And likewise for the probability of A, C, and for the probability of A, B, and C. And we know that the probability of A and B is 0.3, the probability of A and C is 0.5, and what the heck, let's just add them together, and we'll get... Now, we have two probabilities of A. Well, let's just drop one and get a smaller value. But if we really have a probability measure, the sum of the probabilities should be 1. So we don't have a probability measure. Of course, that could just be viewed as bad planning. Let's try some good planning and make something that's a probability measure. So let's try to construct a probability measure. Suppose S is an infinite set of outcomes, but it's indexed in some fashion. And let's make the probability of any individual outcome the ith power of some number p. Let's determine the value of p. Now note that the events consisting of the single outcome, they're all mutually exclusive. Since we want to have a probability measure, the probability of the sample space must be the probability of this union, which is, again, because these events are mutually independent and we're supposed to have a probability measure, that's going to be the sum of the individual probabilities, which is going to be, and this is a convergent geometric series whose sum is, and since we want this to be equal to 1, then we can solve this for p, and we find, and so p is 1/2. Now in that case, we had an infinite sample space, and finite is actually harder. So let's suppose we have a finite sample space, and same setup, the probability of any individual outcome is p to the nth. So, as before, we need the probability of the entire sample space to be 1. Since the events consisting of the individual outcomes are mutually exclusive, the probability can be broken apart, and so we have the equation And unfortunately, because this is a finite series, we don't have a nice way of expressing it. While this equation can't be solved algebraically, we can approximate a solution using somebody's method and get several solutions. However, the additional requirement that we're dealing with a probability measure means that the probability must be between 0 and 1, so P is the solution that's between 0 and 1, and so the only viable solution is about 0.5041.